In this video I'm going to explain with an example the method of proof called proof by contradiction. So not to get mixed up with contraposition or contrapositive, but this is proof by contradiction. And this method is not limited to just proving conditional statements. So we've got direct proof and then its slight variation, which is proof by contrapositive. But here, proof by contradiction, we can extend it to other types of proof. So this is sort of how it works. We start by assuming that the original statement or proposition that we're trying to prove is actually false. Okay, so start by assuming that it's false. So set it up that it's false. And then we use sort of mathematical working steps of logic to show that that assumption leads to some inconsistency or contradiction. So in fact that the assumption we had can't be true, and therefore since the assumption that we had can't be true, since the assumption was false, therefore the original proposition must have been true. Now that probably all sounds like a little bit mixed up. So let's do a proof, and we'll do probably the most classic of all proof by contradiction, which is proving the irrationality of a surd, and our most basic surd is root 2. So we're going to prove that root 2 is irrational by using proof by contradiction. Now, one of the reasons why proof by contradiction is useful here and in other cases is that we don't really have a simple definition for an irrational number other than, exactly as the name suggests, it's not rational. Okay, so we can easily define what a rational number is, but really our definition for irrational is just not that. So what we can do is let's assume, so here's our proof, let's assume that root 2 is rational, because we've got some way of sort of mathematically defining or describing that. And then what we want to do is show that if we assume that we end up with some logical mathematical contradiction, which means that in fact that assumption must be wrong, and therefore root 2 must be not rational, which means we've proved it's irrational. Alright, so let's set up our definition for a rational number. So if root 2 was rational, then we'd be able to write it as the ratio of two integers. That's the definition of a rational number. So a over b, where a and b, so let's be clear on the conditions here, a and b are integers, are members of the set of integers. What else? If it's a rational number, then it must be in simplest form, so we must be able to write it where the highest common factor of a and b would be 1. So that's just a way of saying it's in simplest form, a and b share no common factors other than 1. And the only other thing would be to say that obviously the integer b can't be equal to 0, because then that would be undefined. So that's really the definition of a rational number there. It can be written as a ratio of two integers which share no common factors and where the denominator is not 0. Okay, so let's do some steps of mathematical working with this and show that we do indeed reach a contradiction. So what I'm going to do is let's multiply, let's say multiply both sides by b. So we get root 2b is equal to a, and then if we square both sides, we'll just get 2b squared is equal to a squared. So what that's saying is that a squared can be written as 2 times some number. So in other words, a squared has a factor of 2, doesn't it? So a squared has a factor of 2. I guess another way of excuse me, writing that or describing that would be to say that a squared is even. And we know that if a squared is even, the only way we can square an integer, or any real number rather, and get an even number is if the number itself is even. So therefore a has a factor of 2. Now we could sort of prove that as a separate proof, but we're assuming that's, been proved and shown that if a squared is even, then a has to be even as well. So let's let a be equal to 2 times k, where, k is some integer. So we're saying if a has a factor of 2, or it can be written as an even number, then let's write it as 2 times k. And let's sub that back up into the line just above. So we'll now write 2b squared is equal to the square of 2k. So I've just subbed that a is equal to 2k into this line here. And so I've replaced the a with 2k, and I get that line down there. So let's do some working with that. We get 2b squared equals 4k squared, and therefore b squared is equal to 2 lots of k squared. Okay, so now we're saying that b squared has a factor of 2. Factor of 2, which means b also has a factor of 2, or we could say b squared is even, so therefore b is even. And we've now reached a contradiction. When we look at these two statements here, they contradict this here, which was that root 2 can be written as a over b, where the highest common factor of a and b is equal to 1, or where a and b are already in the form where they have a highest common factor of 1. So we could say this contradicts that condition there. So that leads us to the conclusion that the assumption that it could be written as a rational number is false, and therefore we're left with the conclusion that root 2 is in fact not rational, it is irrational. There's our proof complete. We could whack a QED on the end there. Alright, so it takes a little bit of time to sort of get your head around that. And it's not a natural way, definitely, of thinking about doing a proof. But like I say, in cases particularly where it might be hard to define the thing that we're trying to prove, like to define that a number is irrational, we might have to define the contradiction of that, or the say that's false and the opposite is true, and then try and prove that that leads to a contradiction.